and I have to hit record. It doesn't automatically record anymore. So if you were wondering and you were watching the replay, take a screenshot. You missed number 27 and 28. Sorry. All right. Okay. Are you good on that one, Rudy?
Yeah, I'm all good on that one.
Okay. Good. Any other 17.1 or 17.2 questions? I think it's funny that the picture they took for this, like it has like this glare on it. Like where was this? Like, so it looks like there's glare like behind me. Maybe it looks more realistic, like there's actual glare behind me. I don't know, it's weird. Any other homework questions? 17, Christian asked about 17.251. All right, 17.251, work integral, okay. All right, 51, work integral. So there's our force field. So it's just fun to say that, force field. But it's a vector field that is each of the vectors represents a force. And we're moving on the parabola. Whoa, what just happened? We're moving on the parabola y equals 2x squared from 0, 0 to 2, 8. So very detailed sketch here. So this is y equals 2x squared. You can kind of draw the field here. You can see this is a radial, this is not a radial field because I was thinking xy. So this one, they've switched it, yx. It's a little bit harder to draw. Maybe I have Maple open, maybe we'll pull it up. But the question is, we're gonna move from 0, 0 to 2, 8, and we're wondering how much work is done by this force field moving an object from 0, 0 to 2, 8. The first thing we need to do is parameterize our curve. And so we talked about this. This is a perfect example of like one Rudy had asked. We'll just do t and 2t squared. And with that in mind then, what would be the bounds for t? Christian is correct, 0 to 2. Now to your question, Mike, could it be y equals x cubed? That depends. It depends. So are you thinking of 17.3 where we did the videos and the path didn't matter? Is that what you're thinking of?
I actually didn't watch those videos yet, but
okay.
I mean, just looking at it, I saw 2 and 8 and I'm like x cubed.
So here's the thing. It depends on the field. For some fields, it doesn't matter how you get there. It'll always be the same answer. For other fields, it does matter. And there's a test. And in fact, the type of field is a conservative vector field. And that's what section 17.3 is about.
Got it.
So in this case, this is a conservative vector field. And so in this case, it would be correct. But that's the reason why. It's because it's a conservative vector field. Yeah.
Got it.
Yep. So you'll watch that video and you'll see like, hey, look at that. I'm so smart. I knew that was true even before I learned it. All right, so for us here, our total work is going to be the line integral over the curve of the force field dot product with dr. So we're going to go 0 to 2. The field is yx, but I'm going to use we're looking at the field just on the curve. So it's y, 2t squared, x, t. And then the dot product with dr, if you recall, is r prime of t dt. And so let's see, that will be 1 and 4t dt. And then we do the dot product and we get a nice polynomial. Oh, even better than that, 2t squared. Well, it's technically still a polynomial, I guess, but it's just a monomial. Integral from 0 to 2 of 6t squared dt. I'm sure everybody can do that. So Christian, does that clarify the question that you had for that one?
Yeah, I think where I was most confused was the force that had a y and then the x. I didn't know
Yeah,
what
yeah.
to do.
What that means is if I pick a specific point like -1, 1, remember the force is a field of vectors. I mean, that's why it's called a vector field. So there it's all these infinitely many vectors. And the size of the vector, the direction of the vector, depends on the point. And so if I pick the point -1, 1, the vector when I'm there is, well, it's the y coordinate and then the opposite of the x coordinate. And so when I'm at that point -1, 1, the vector is 1, 1. 1 in the x direction, 1 in the y direction. If I pick the point over here, like say 2, 0. So 2, 0. The vector there would be the y coordinate, 0, and then the opposite of the x coordinate, so -2. So there the vector would be 0, -2. Let me show you what this looks like here with plots, and then it was field plot, I believe. Oh shoot, what does these look like? Oh, I can't remember. I feel like it's brackets, y, x. Nope. Hold on. I need to cheat and get the help file for field plot. What do they look like? All I do is scroll down to the bottom and like show me an example, and then I'll just copy it. Field plot, bracket, oh, then I need an x and a y. Okay. All right. And so let's do, we don't need it very big. X equals -2 to 2, maybe -4 to 4. Y equals -4 to 4. There we go. And there's our field plot. And so our object moved from 0, 0 to 2, 8 along that path. In fact, we could display them together. Display field plot 0, 0. Let's go y from -8 to 8. And then we can also add in a plot. And I'm pretty sure this is how you do a plot, 2x squared. X goes from 0 to 2. Cool. That looks good. And so that's what, did I do that one wrong over there? Because didn't I say at 2, 0, it would be, oh, didn't we switch? I didn't put the right vector field, did I? Oh, y, x, why was I doing the opposite here? Does anyone know why I was doing the opposite? I have no idea. I probably really confused Christian there. Let me try that again, because those are not correct. So to Christian's, his question was about like, I don't understand the y-x. So now I need to fix this because that was not correct. I guess that's why you use Maple to check your work. So we have the point here, -1, 1. The vector there is you switch them. So the vector there is 1, -1. 1, -1. And I was over here at 2, 0. The vector there would be 0, 2. 0 in the x direction, 2 in the y direction. So that should be over here. Now they're scaled. You can't really see here because if they had them as long as their actual length, they would just like totally jumble it up. So they're scaled, but you can see over here it's going there. See how they're coming down? So it's going down over here, and here they're going up over here, and so it's going in the right direction. Now that's how I knew, like, wait a minute, my vectors aren't going in the right direction. Incidentally, we will see that you should get a positive answer here, and I don't even need to look at the integral to know you'll get a positive answer. That's because the arrows are generally in the direction of motion from 0, 0 to 2, 8. And so that will give you a positive answer. That's the work done by the field moving from 0, 0 to 2, 8. If you move against the field, it's not the work done by the field because the field is moving against you. It's the work that you would have to do to move the object against it. So that would be if we started at 2, 8 and went to 0, 0. All right, sorry about that confusion, Christian. I hope that helps a little bit about what the y-x is. It's a field of infinitely many vectors. And what that y-x is, that's telling you this is what the vector is at each point. It's the y, you switch the x and y coordinate, and that's the vector there.
Okay, yeah, that makes a little bit more sense now.
It's almost confusing. It would be easier if it like gave you a formula for the x and a formula for the y. Then it would make more sense. It just seems weird that they just switched them. Like, how did you just switch them? But they're just functions. Technically, vector fields. They're functions of x and y. And it's some function for the x and a different function for the y. They're just, each coordinate is a function of x and y. Okay, we're working on homework here. Any other 17.1 or 17.2 questions?
I had a question on number 62. I'm having a little trouble visualizing what the graph would look like, the crosswinds.
Now, is this is just a 2-dimensional one, right? Like you could, like real flying is 3-dimensional, but I think they make this one simplified a little bit. Okay, an airplane flies in the xz plane where x increases in the eastward direction and z greater than or equal to 0 represents vertical distance above the ground. A wind blows horizontally out of the west, producing a force F equals 15, 0. On which path between the points 100, 500, and negative 100, 500 is the most work done overcoming the wind? Okay, so drawing was your first question. So let's do a sketch. We're doing X, Z. So in your 3-dimensional, we're in this XZ plane. That's where we are right now. We're in the XZ plane. Okay, Z greater than or equal to 0, that's fine. Path between, X increases in the eastward direction. This is east, this is west. 150. And then we're going to negative 100. And 50. Okay. Our field is actually constant, 150, 0. So what that means is our field everywhere is in the positive x direction, and this is not to scale because they should be 150 long. So the whole field is actually just constant. It's just pushing against us, and because we're going to try to fly from, we'll call it point A to point B. We're going to try to fly from point A to point B. Okay, so we have 2 options, and we're going to find the work for both of these. One option for A is that we fly on the straight line. We just go boom, like that. And they even give us all the parameters. So what they do, they kind of make it a little bit easier for you. They say, I'll use R of t to be negative t 50, and then t goes from negative 100 up to 100. So you just do the line integral, negative 100 up to 100. The field dot product, actually we can just put in the field, right? It's 150, 0, 150. And then the dot product with r prime of t dt. And then for B, it's the same question about work, but it's a different path. It's the arc of a circle. And again, they give you the R, they give you the R of t. I think it'd be a more interesting question if they didn't. So they did save you a little bit of pain there. From 0 to pi. So they give you the intervals of t and everything, And so that would be, let's see, 100 cosine of t, 50 plus sine of t. That would be the semicircle going up. And again, you can find the work done just by finding the line integral. This time it's 0 to pi. Again, 150 comma 0, dot product with whatever r prime of t is, dt. So the question is essentially, if you're flying against a headwind, because that's what's happening here, the field is blowing directly against you. If you're flying against a headwind, do you do more work flying straight into it or kind of flying up and over it and then back down? Now you're still flying against it. So the question is, which way will you do more work? And there's 2 different integrals. The answer should make sense when you're done. I'll just say that. So I know you were just asking about the picture max. We did a little bit more than that. How does that?
Yeah, I drew it like that. I just wanted to make sure it wasn't something that was in 3D that I just wasn't quite sure,
Right.
Okay.
Yeah. You could certainly make this same problem and then add more information and have it be, 3-dimensional. But the key is that the airplane is flying in the XZ plane. So that's how we know it is just 2D. Yeah. All right. Good question. All right. Good. Any other questions? 17.1 or 17.2. We can do 16.5 if you found one there that you wanted to ask about. I have that up too.
You just scroll down a little bit. I'm still kind of copying.
There we go. I really wish I was on top of things and not kind of overwhelmed with other stuff, because it would be nice when I posted these to put in the comments like I do for the exams, like question 1, question 2. And then I could put, skip to 17.2, number 62, and you could kind of like skip to each part of the replay. But sorry. Okay, we're still looking for questions. Any other homework questions? All right, I'm not seeing any. So let's do, I think we had 1 or 2 examples left over from the 17.2 practice. Yeah, again, these are just ones from the homework I just pulled up for some extra practice. All right, so we're gonna do number 42. This one is just a line integral. And okay, so we're gonna find the line integral of f dot t ds. And really we don't use that to do it. What we do instead is do f dot dr, which is really f dot product with r prime of t dt. That's the version that we actually use to compute it. So let's see here. F is, the field is negative y comma x. And so we want to look on that particular path. What is y? What is x? That will be negative 4 sine t, and then x is 4 cosine t. Then we'll do the dot product with r prime, negative 4 sine t, 4 cosine t, dt. And this one's nice. They give us the t interval, so 0 to pi. All right. And so now we'll take that dot product. 0 to pi, and we get 16 sine squared t. Oh, that's convenient. 16 cosine squared t dt. You can factor out a 16. That's sine squared plus cosine squared. That's 1. So you just get 16 dt. And that's 16t from 0 to pi, and that's 16 pi. Nice. Does not get much better than that. Because you're going to have a formula sheet and you'll have that formula down, I'm probably not going to give you a bunch where the R is given to you because it's just not really assessing anything. It's just too easy to do that. So I'm more likely to describe the path and give it to you that way, because then at least you got to figure out what is the path to Rudy's question about the homework. How do I know where T starts and T ends? And because if you have this, all this information, you're just kind of plugging stuff in the formula. Now there's some skill to that. So it's not like we would maybe have one of those maybe, but we won't have a lot of them like that. It just doesn't assess very much. Okay, last one. Let's see here. So consider the following vector fields and the closed oriented curve. Okay, so we have a circle, radius 2, circle radius 2. And it looks like the unit circle, but going in the opposite direction. So it starts here, and then it kind of loops around. You can see the directional arrows. And so we're going to make a conjecture about whether the circulation is positive, negative, or 0, and then compute the circulation. Let's pop over to the notes just to remind you what the circulation is. That would be 17.2, and I think it's like on the last page. There we go. So the circulation is just the line integral over the curve, but it's a complete closed curve. So you do the line integral over the complete closed curve. Okay, so let's go back, actually, let me go back to that so we can make our conjecture. Why does it go back to the top? That's annoying. Okay, so the circulation is a measure of how much of the vector field points in the direction of C. So we want to go back to where we were, and we want to know, just make a conjecture. Just make a conjecture looking at the path as we move around the path, and we're looking at how much of the field is in the direction of our movement. The question is, do we think it's positive or negative or 0? So let me see here. Oh, because my account changed, now I can't do polls. I was paying for like the pro upgrade, but then they said they would give educators free access, but then there's not everything in there. Okay, so we're gonna cheat the vote. We're gonna look under, remember under the manage participants? There are participants, and you can like click different things. So we're gonna go, if you think it's going to be positive, give it, I can't draw a thumbs up. Thumbs up? Does that look like a thumbs up? I don't know. Negative, thumbs down. And then the 0, what should be 0? No. Okay. Those are your 3 options. So if you think the amount of the field that's in the direction of C will be positive, go under participants, and then there should be a little thumbs up option in there somewhere. I think it's under the more for me at least. I don't know if I show you this. Can you see, like I have a more thing, and then there's some other stuff that pops up. Somebody, Max put a coffee cup. What does that mean, Max? That wasn't one of the options. All right, lots of people think it's 0. Interesting. That's plausible. That's plausible. Ty thinks it's 0 in the chat. So lots of zeros. Okay, lots of zeros. Everybody said 0 who answered. Okay, I cleared those. Oh, there's another one, Nathan. Sorry, I just cleared it. Anyone want to explain why do you think it's going to be 0? The majority said 0. Everyone who answered it. Anyone want to give a thought?
It kind of looks like the same forces are opposing each other a little bit.
That
Like,
makes
you could
sense.
just look at it.
Mm-hmm.
It's like they're symmetrical but opposed. Like, I don't know. That's
Yeah.
why I thought 0.
I was going to say the symmetry too. You know, if you go like, oh, hey, look over here, I'm with it. So there'd be some positive there. But then there's like the same amount on the other side that's against it. And then, oh, look, I'm with it again. That's positive. Oh, but then there's the same amount that's against it again. So I think that does make sense that it would be 0. So it probably will be 0. Let's see. Let's compute the circulation. The circulation will be just a line integral. That's all it is. And it's just circulation because you go all the way around. Okay, let's see. We have, this is a nice one. It gave everything to us, 0 to 2 pi. F is, ooh, we got to do some work here. Y minus x. So that's 2 sine t minus 2 cosine t. And then I'm looking over at the force field here. Y minus x and then x. So 2 cosine t. And then the dot product with r prime, negative 2 sine t, 2 cosine t dt. Any questions so far about how we set that up? All right, let's keep going. Multiply negative 4 sine squared t plus 4 cosine t sine t. It's a little awkward to multiply those together. I think that looks good. Negative 4 sine squared plus, yep, okay. And then plus 4 cosine squared t. Oh no. dt. Oh no, that's not good. I was hoping to get sine squared plus cosine squared again. Let me double check. Yeah, it's definitely positive 2 sine t because it's y minus x. And then over here, it's definitely negative 2 sine t. Shoot. Already got your trig identities? Integral 0 to 2 pi. I would put the 4 cosine squared t with the 4. Actually, let me factor out the 4. So we'll put a 4 out in front. How about that? 4 out in front, 0 to 2 pi, and then we have cosine squared t minus sine squared t plus, I'm going to write it sine t cosine t. That one's easy. The second one, you could, that sine t cosine t, just do a u substitution, right? Any thoughts about the cosine squared t minus sine squared t? Only trig masters need apply here. What do you remember from your trigonometry? It's not one you use very often. Quick, Google trig identities. Okay, I'm 96% sure that's the cosine of 2t. That was not good. Huh? Really awkward, ugly formatting. This is probably from like 1994 and hasn't been updated with the new math syntax. So cosine of 2x is cosine squared minus sine squared. Now in your defense, I did teach trig 10 years ago, so that's why I remember some of these. So cosine 2t plus sine t cosine t, and now they're each just u substitutions. So
I'm sorry, I didn't mean to interrupt.
no, go ahead. Yeah.
Getting something. I don't know if I did the dot product wrong or something.
Well, one of
but-
us did, so it could be me. Could be me. What do you think? What do you notice?
So like when I did the dot product, I like distributed the -2 sine t. So I got -4 sine squared t plus 4 cosine t sine t. And then when you distribute the 2 sine, you get -4 cosine t and sine t. So don't those cancel out? And then you get plus
no,
4
see, remember for the dot product, you're only multiplying a times c and b times d.
Oh yeah, okay.
Yeah, it's just we haven't. We're just starting to do those again, right? It's been like a month and a half since we did dot products, but
Yeah.
cool. All right. So now this one, I'm just going to do this one mentally. That'll be 1/2 sine of 2t. You can check when you take the derivative, you get cosine of 2t times 2 because of the chain rule. And then the sine, that'll actually be 1/2 sine squared t, because you'll have a u equals sine t, and it'll be integral of u du, and so you'll get 1/2 u squared. So that's where that one comes from. And you can do those u subs off to the side if you need to. Oh, Rose, I just saw your comment. Oh, you had it. You had it, Rose. I saw it. I wish it would alert me when there are comments, but maybe that'd be annoying if I got beeped all the time. It is distracting when I'm talking and like somebody has to leave or their connection goes out and they leave, and then I'm like dinged. I'm like, oh, who left? Someone left. Nah, but it's anyway. So this will be, I guess we could just call it 2, right? Because they both have a half, so we could just call it 2. Sine of 4 pi plus sine squared of 2 pi. Wait, these are all just zeros. Minus sine of 0 plus sine squared of 0. So Michael was right. I mean, you all were right. Everyone is right. They're all everything's just 0. So we were right. 0 circulation. That's it. We're done. Any questions on that one? All right, I'm going to move a little bit into 17.3 then. I have a few extra examples there as well. And I know some of you haven't watched this, especially because tonight's homework is through 17.2, so it's totally understandable. Maybe let me just pop over to the notes and show a couple of key facts. These are, okay. So this is all about conservative vector fields. And here's the test for conservative vector fields and what the definition is. So a conservative vector field is basically a vector field that is the gradient of some function. We call it a conservative vector field if there's some function where that r vector is its gradient. That's what it means to be conservative. And then the test for it is basically like cross partial derivatives. So if you have a 3D one, you can see there's 3 different equalities you check. Is the partial derivative of f with respect to y equal to the partial derivative of g with respect to x? And you see how they're like cross? And then f with respect to z, and then h with respect to x, because h is the z one. And so you kind of, all these cross partial derivatives have to be equal. That's the test. And if they are, then it means that your field, you can like work backward and figure out what the original function must have been that the gradient came from. Those are the 2 examples I wanted to do today. If you're a little lost on that, I think just take some good notes in the examples today. You might even pick it up from here if you haven't watched those videos. I think take some good notes here, and then I think when you watch the videos, it'll all come together. So don't stress out too much. So first, our test for a conservative vector field. Here we just have two functions, or it's 2D. There's an f and a g. So here's what we're going to do. We're going to do the cross partial derivatives. So we're going to find the partial derivative of f with respect to y, and then we're going to find the partial derivative of g with respect to x. And to be clear, the f is the 2x cubed plus xy squared, and the g is the 2y cubed minus x squared y. So why don't you take a couple moments and see if you can find those partial derivatives. Take the partial derivative of the 2x cubed plus y squared, take that partial derivative with respect to y, and then look at the 2y cubed minus x squared y, take that partial derivative with respect to x. When you're done, why don't you use the yes or no box. Is it a conservative field? Are those equal? Those two should be equal if it's conservative. So when you're done, you can go under the participants and then do a red no or green yes.
Do you take the partial of just like, so is it the vector, like the partial of fy and then the partial of gx?
What you're going to do is you're going to take the partial derivative with respect to y of just the x component of the vector.
Yeah.
Just that.
And then for g of x, it's just for the y component?
Correct.
Okay, got it.
This one's kind of mean, isn't it? It's like so close. I see some no's here, and you are correct. It's really close. You get, with respect to y, you get 2xy, and with respect to x, you got the negative there. It's negative 2xy. So no, this field is not conservative. Okay. All right. Let's clear that. Any questions on that one? Okay, next one. We're going to start the same way. We're going to determine whether it's conservative. And if it is, then we'll find a potential function. Now this one is three-dimensional. There's an f, there's a g, there's an h. So we need to see, is the partial derivative of f with respect to y equal to the partial derivative of g with respect to x? And we also need, all of these have to be equal. The partial derivative of f with respect to z is equal to the partial derivative of h with respect to x. You see how we're cross-matching? F is the x component, h is the y component, and so we're doing the cross partials. And we also need to see, is the partial derivative of g with respect to z equal to the partial derivative of h with respect to y? And again, you're cross-matching those. You're trying, g is the y component, h is the z component. So you're doing the cross partial there. So again, give you a few moments and check to see if we have, go ahead and do a yes or no for this one. All three of those have to be true. All three have to be true. One answer so far. Couple, we got Max and Kyle say yes. Let's see here. Let me write a couple steps out. The partial with respect to y of yz, that would just be z. The partial with respect to x of xz, that would also be z. So that one's good. That one's good. Partial with respect to z of yz, that one will just be y. And then the partial with respect to x of xy, also y. Okay, good. And then partial with respect to z of xy. Of xz, and the g there. That'll be x. And is that equal to the partial derivative with respect to y of 8xy, also x? Okay, all three are yeses, so it is a yes. Okay, so here's the key. So, yes, F is a conservative vector field. Here's the logic. What this means, there is some function phi of x, y, and z, and yes, phi was already used as like spherical coordinates. Sorry, they ran out of letters. I don't know, it's standard notation. So there's some function phi of x, y, and z, so that our field F is actually the gradient of that phi function. And as a reminder here, the gradient is the partial derivative of phi with respect to x, partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. And keep doing implies. This implies then that our field F, which is yz, xz, xy, must be equal to the partial derivative of whatever this phi is with respect to x, the partial derivative of phi with respect to y, and the partial derivative of phi with respect to z. So our challenge now is figure out what phi is. That's our challenge. Find phi. Now, I should say find a phi. There are, in fact, infinitely many. We just need to find one. But they all look really similar, and the only difference is very minor. So we will see that when we're done. All right, here's how we do this. Look at those fields. The x components must be equal. So that implies that the partial derivative of phi with respect to x must equal yz. Well, if that's the partial derivative of phi with respect to x, then phi must be the integral of yz dx. Now, in this context, y and z are just constants, and so all we get is x, y, z. But there could be some other function out there, and the nature of that function is really important. It's not just a constant. Does anyone have any idea about the nature of this other thing out here?
Isn't it just like some arbitrary like vector?
It's not a vector. Phi is a function. So it's a function.
So it'd be like a function of x, like a plus an f of x, or
You're close. Christian, did you want to add something?
I feel like it could just be y or z.
Yes. Why did you say that?
Because they're considered constants when you're taking the derivative of x.
Right? So we would lose them in the derivative. So it actually can't be a function of x, because then it would have been in the partial derivative. But it could be some, usually I think our book still uses a c, but they call it a function. And to Christian's point, it's some function of y and z. Because he said, right, y's and z's would be constants. So when you take the derivative, it would just go away. If it was a function of x, it would still be in the derivative, but it isn't. There's no functions of x in there. Okay, our challenge now we need to find that c. So here's what we're going to do. We're going to take the partial derivative of our new phi that we found and take its partial derivative with respect to y. That'll be xz plus whatever this partial derivative of c with respect to y is. But we know what the partial derivative of phi with respect to y is. It's up above. The partial derivative of phi with respect to y is the y component of our field. So this must be equal to xz. Now here's the thing. This must mean that, whoops, go back to blue. This must mean that whatever that partial derivative is of c with respect to y, it must be 0. Well, if the partial derivative of c with respect to y is 0, what does that mean that c must be equal to? Ooh, this is a big leap. Well, maybe not. We have some function of y and z. Some function of, it's just a function of y and z. That's all we know. We know its partial derivative with respect to y is 0. What must be true about that function then? I actually want to use similar logic to what Christian used previously.
Would it be xz or some constant?
Yeah, either a constant or a function of z only. Yep, exactly. Let me write it down below here. So c must be a function of z only. And it could be a constant function, to your point. Like, it definitely could be constant. So I'm going to say c must be some, I'm going to use, well, I guess d, just some function d of z. Okay, so that means that our phi function is x, y, z plus just a function of z. Just z only. Can't be a y in there because the partial derivative with respect to y was 0. If you've, I don't know what the 17.3 didn't have very many views, so I don't know if anybody's watched it yet, which is okay. Does anybody know where we're headed next? Can you feel it? You see the thread here? Okay, we started with equating the partial derivative with respect to x to the x component. We found a phi. We took its partial derivative with respect to y, set that equal to our second component. Well, the only one left is the partial derivative with respect to z. That's xy plus whatever d prime of z is. I don't need a partial derivative because d is just a function of z. That must be equal to the third component. Circle those in red. That must be equal to the third component of our field, which is equal to xy. Well, that means that d prime of z is also 0. So what does that mean about d of z?
It has to be a constant.
Got to be some constant. And then we are done, and I'm out of space. So therefore, our phi function as a function of x, y, and z is xyz plus some constant. And this is where I was saying earlier that we want to find just a generating function. There are infinitely many because of the plus c. And usually we use c equals 0. And we just say, well, let's let phi be equal to x, y, z. And you'll see later, this is actually the next example. I don't know if we have time for it today, but the plus c becomes irrelevant. It really doesn't matter for the context that we are interested in. How could you check to know if this is right? Any ideas? Partial derivatives, yes, Christian. Let's be specific. Which partial derivatives and what are we really finding? I think you're right, but I just want to make sure we know what we're doing.
The partial derivatives of what you just boxed.
Sure.
They match f.
Yep. Because remember, the whole point is really, does the gradient of phi equal our original field? That was the whole point. And so that's indeed the check. And so you can do the gradient. The partial derivative with respect to x is yz. The partial derivative with respect to y is xz. And the partial derivative with respect to z is xy. And yep, that checks. That is indeed f. Okay, any questions on that one? Oh, it's time for my afternoon coffee. I have an hour-and-a-half meeting after this too. Fun stuff. I don't know if you can tell, I think it's getting shaggy. I'm gonna go for like the quarantine beard. I'm gonna really try to see how long I can get it by the end of the semester. Let's see. It's looking very gray. I look old. It's okay. I am old. I have a birthday coming up here. I'm not gonna tell you the number. All right. Gosh, we only have a few minutes left. Let's hold off on this last example. This would be a good one to touch base and kind of use as our practice on Monday. Yeah, especially because you're going to be focused on the 17.1 and 2 for the homework tonight. Let me pull up the schedule again, not our webpage from the 90s. So our schedule, we have 16.5 through 17.2 homework is due tonight. We're going to do one more section. 17.3 will be included on our next exam. And I guess I could have had it posted Tuesday. We said, though, I don't want to change. I keep changing my plans. I don't want to change them. So I'm going to post it Thursday, a week from today, and it'll be due on Friday. And that'll cover 16.1 through 5, and then 17.1 through 3. And then next week, I know this is like the lag time to give you time to get your homework back and do an extra review. I have on my list to get a practice document up for you. But we will continue working in chapter 17. Now, the nice thing is a lot of it overlaps. So we'll still get more practice with line integrals and stuff. So it'll be good practice. But yeah, we'll dedicate next Thursday to exam review. Okay, any last questions before we sign off for the day? All right, I am not seeing any. Email me if you do have any questions or post them in the Discord. I'm going to sign out and I will post the replay later in case you missed something. Yeah, all right, that's it. Enjoy the rest of your Thursday here. Have a good long weekend, work hard, and I'll see you Monday.